Okay. Were there any questions from last time? So we were talking about the notion of symplectic quotient, and in particular the case of toric variety. So the theorem was that suppose that Gx freely on the zero level set of the moment map, then the symplectic quotient is binary to 0 mod G. This is a symplectic, also a symplectic manifold. Okay, and the example that we were talking about was the example of toric manifolds. So one way of getting these is to say, well, take Cn, considered as a symplectic manifold, and look at the action of U1 to the n. So this acts on M with moment map the jth component of the moment map is the norm j squared over 2. And then suppose you have a subgroup with G itself a torus, but of smaller dimension, generated by some vectors C1 up through CK in Rn, which we identify with the Lie algebra of G. So then the moment map for this subgroup is going to be given by these pairings of the phi with the vectors Cj, but I always get to adjust by some constant. Cj, so if I take the reduced space now, this is now the the quotient by G. This one of the addenda to the Meyer-Marsden-Weinstein theorem that we said was that there's a residual action because the flows of U1 to the n upstairs commute with the action of G. All of these groups are abelian. These flows upstairs descend. So let's call this moment map that we get on the reduced space phi red. And then the image of M red under phi red, well, it's the tuples in R to the n bigger than or equal to 0, such that the pairing of lambda with each psi j is equal to Cj. Through j equals 1 up through k. So this is called the moment polytope. Of M red, and the picture is that, well, you're taking something that's like an orthon, and you're taking a slice of that by setting some collection of qualities, the pairing of lambda with some CJs should be fixed. So this would be like a typical slice. So this would be the case when M red is CP2. Okay, and then we stated the theorem, which is due to Danilov and Jerkovich. That if I look at the cohomology of M red, then this is generated by the inverse images of the facets with two kinds of relations. So first of all, there are linear relations. For any element of the kernel of the map from Rn to G dual. So G, you can think of this as C as a matrix, and then this would be the transpose of this matrix. So an example of this would be, suppose that C just has a single component given by 1, 1, 1. And then the kernel contains of the dot product of 1, 1, 1. Contains the vectors 1, minus 1, 0, and 0, 1, minus 1. And so in CP2, you have these three facets, F1, F2, and F3. And so I would get that when I take these cohomology classes, I get 0, and the same thing for F2 and F3. So this says that the three facets of the moment polytope of CP2, they represent the same cohomology class in H2, which you expect because you know H2 of CP2 is just one-dimensional. Okay, so those were the first kinds of relations, and then the second kind of relations, these are nonlinear relations. And the nonlinear relations say that whenever you have some collection of facets whose intersection is empty, then the corresponding cup product, of these cohomology classes is 0. So for example, if M red is CP2, I take I could be 1, 2, 3, and then F1 and F2 and F3, they have no common point in intersection. And this means that when I take the product of all of these, I get 0. Okay, so the conclusion is that if I take the cohomology of P2, it's generated by a single line. Let's call this class L for short. And there's a single relation, which is that L cubed equals 0. Let's do another example. So suppose now M is C4. And now I take the 2 torus generated by 1, 1, 0, 0 and 0, 0, 1, 1. This is a little sloppy. So this is supposed to be my second vector. Okay, so then if I look at the moment polytope, I'm looking at 2 equations, lambda 1 plus lambda 2. Let's set it to be, say, 1. It doesn't matter. And lambda 3 plus lambda 4 is equal to 1. So this is sitting inside R4, the non-negative wheels. So what's MRed in this case? Am I allowed to ask the audience, even though it's on Zoom? You can write in the chat if you can see what this is. So the polytope is going to be, well, lambda 1 can go from 0 to 1. And lambda 3 can go to 0 to 1 as well. And then once I know that, then I know what lambda 2 and lambda 4 are. So this thing here is a square. So I want to know what the polytope for a square is. What happened to my chat? Okay, let me come back to the question. Yeah, Nuno says this is the general of Djokovic's theorem. Yeah, so MRed, I'm setting z1 squared plus z2 squared to be some constant. The way I have it normalized, I have it like this. And then I'm taking z3 squared and z4 squared. And then I'm modding out by s1 squared. So this is going to be the complex projective line, but 2 copies of it. And so if I look at the polytope polytope, looks like this. I now have 4 points Vortices, to match with my conventions, I have to number them like this. So what will the relations be here? Anything that's perpendicular to the C's will give me a relation, right? 1, 1 minus 1, 0, 0, for example, or 0, 0, 1 minus 1. Okay, well, in P1 times P1, the facets which are opposite to each other are equivalent in cohomology. So F1 and F2 if I think about this in the product description, both of these are just a point times P1, but I'm changing the point. So they define the same relation in cohomology, and the same thing for F3 and F4. So those are the linear relations, and then the nonlinear relation will be if I take the opposite faces. F1 and F2 don't intersect. And the same thing with F3 and F4. So if I call this class L1 and this class L2, then I get a description of P1 squared as having two generators with the relation L1 squared and L2 squared are both 0. Of course, what I expect from the Finite formula. Yeah, so the question of why there are no other relations, I never found the Danilov-Jerkovich theorem. I mean, it's an induction to show that there are no other relations. One of the nice things about going to quantum cohomology, which we'll do in a second, is that the relations become much more natural in the sense that you can see right away from a well-known theorem, at least in the final cases, that the number of relations is correct. Okay, so I want to move on now to equivariant cohomology. So I'm not gonna assume that people have seen this. I'm gonna first talk about this in the Duran law. So that let N be a manifold with an action of just the circle group, and then this has some generating vector field for the action. And so that then the Cartan relation for this this vector field says that if I take dIx plus IXD, this is the Lie derivative with respect to x. But one thing you can immediately strikes you when you look at this formula is it looks like the cross terms in the expansion of d plus ix squared. And the cross term is the only thing that can possibly not vanish because d squared and ix squared are both 0. So let omega m g be the space of g invariant form. So that's the same thing as saying all of the betas in forms on M such that the lead derivative of beta is equal to 0. So then d plus ix squared is 0 on the space of variant forms. So you can try and use this to define a chain complex. It's convenient to throw in a formal generator to get it to be graded. So let t be a formal parameter. And so then the space of equivariant forms is the space of invariant forms with this additional t thing. And then we define dg to be d plus I of x times t. So if you set t here to be degree 2, then this operator is still degree 1 because the d has degree 1, the ix has degree minus 1 that you're multiplying by a formal variable that you decide has degree 2, so the whole thing still has degree 1. And then dg squared is 0, and so you can take hg of m to be the kernel of dg modulo the image of dg. You know, how's the microphone? Is it sort of okay?
Yeah.
Yeah.
I think so.
And so this is functorial. For equivariant maps. So the usual way you prove this is by using the Cartan relation again. Here, if you have an infinitesimal equivariant map as an invariant vector field, and if I look at the lead derivative of this, I can write this as dg iy plus iy dg. The point is you have an additional term coming from ix, but the ix and the iy cancel each other out when you multiply this out. So you have an equivariant Cartan relation, and that tells you that this thing is homotopy invariant for equivariant homotopies of equivariant. Okay, so that's the first observation, and the second observation is that suppose that gx freely on M, and then in this case the equivariant cohomology is just the cohomology of the pool. Well, how do you see this? Well, suppose I have an equivariant class which is closed under DG. So I can write out the components of beta in a chain. So to say that the beta is closed means that well, there are two parts of the operator. There's the D operator, and then there's the IX operator. And the fact that the whole thing is closed, well, it means that this piece up here on the upper left, it has to go to 0 under D. That's the piece that has the smallest power of T in it. And then this piece on the right, it has to go to 0 under IX. But the other terms just have to go to 0 when you combine part coming from the vertical and the horizontal piece. Okay, so now the point is that you know, because it's acting freely, you can think of it as a bundle over MG. So I can take a connection form for the action. And then I can let gamma be the connection form times this last part, the D minus K here. And then I can take beta minus dg gamma. And the point is that the I of x applied to gamma, because the beta d minus k goes to 0 under ix, I just get the contraction of the first part. And because it's a connection 1 form, this is just 1. So gamma here, if I subtract off dg of gamma, that's going to kill this last part in the chain. It's going to change the next to last part, because the d of gamma is going to be non-zero. But then just by induction, now I've lowered the degree. Beta minus dg gamma is the chain of smaller length. And by induction, I get that the cohomology class of beta is the same thing as the cohomology class of a beta prime, where beta prime just has length 1. So what does that mean? So that means that both d beta prime is 0 and ix of beta prime is 0. But this means that beta prime is a pullback. Of some beta double prime, a form on n mod g. So this shows that the natural map from forms on G into equivariant forms on M is surjective in cohomology. And the injectivity is easier, so that's an exercise. So what's the generalization now to compact connected V groups G? Well, I define the space of equivariant forms to be the space of polynomial maps from G to forms on M, which are G invariant. And I said dg of the form beta. So beta was a polynomial map. dg beta is also supposed to be a polynomial. So first I take d of beta of c, and then I add or subtract. I'm going to change the sign here. So this is a minus sign. This is just a convention. Minus, so then I contract the generating vector field for C into beta of C. And so then Hg of M is this operator squares to 0, and Hg of M is the kernel of dg modulo the image. So this is the equivariant homology of M. And notice that one thing I can do here is I can just take polynomial maps, polynomial functions on G, which are G invariant. This naturally sits inside polynomial maps to forms, and this subspace is DG closed, because I'm just talking about constant functions. So d of these things is 0, and constant functions are 0 forms, so the contractions are also 0. And so the space of invariant polynomials maps to the homology. So what's an example now? So suppose now that M omega is symplectic. A moment now. So with the G action. A moment map for the action is equivalent to an equivariant extension of omega from two forms to equivariant two forms. Why is that? Well, to say that the contraction of omega is d by c, this is the same thing as saying that when I take dg of omega plus phi, then, well, what are the terms when I multiply this out? Well, the first term is the d omega. That's automatically 0. And then I have terms which look like ICM omega plus d by c. But I put a minus sign here. in my convention, so that the vanishing of these middle terms will be equivalent to this moment map condition. And then I have a final term, which is the contraction of ICM with IC. But this is just 0 for degree reasons, because you can't contract the contraction of a 0 form with the vector field is equal to 0. So this would be a typical example. Okay, so now we can state the Kirwan surjectivity theorem. Suppose M is compact. So some proper cases are also okay. Then I'm assuming that I have a symplectic form and a moment map, so that GX freely on phi inverse of 0. And so then I have these maps which go from the equivariant cohomology. First, I can just restrict to the 0 level set. So the inclusion of the 0 level set in M is certainly an equivariant map. So this is using functoriality. And then we said in cases when GX freely, this is just the cohomology of the symplectic quotient. And the claim is that this is surjective. And there's a little addendum to this, which is, remember that I had polynomials on G mapping to equivariant cohomology. And the Kirwan map is the map on the right. Well, I also have a map from polynomials to H of M red. So this is the Chern-Weil map for, if I can think of the 0 level set as a bundle over M red. And this diagram means, i.e. the Kirwan extends Chern-Weil. So we actually almost proved this in the case that G was S1. Because in the case G is S1, polynomials are just these are just these functions of this single formal parameter T in degree 2. And so what happens to the Kirwan map? What's the Kirwan map applied to T? Well, we said that you make it into a chain of length 1 by subtracting off dg of some connection 1 form. So I change T to t minus d g of alpha times t. But now I made this change in sign convention, so it becomes plus sign. And this will cancel off the t parts, but just leave me with the d alpha. And then I said that this maps to this form descends under the map phi inverse of 0 to the reduced space. This is an S1 bundle, where if you take D of a connection and you descend it, that's exactly what we mean by the curvature of this bundle. And so this map, which takes a formal parameter and then maps it to a curvature, this is exactly the definition of the Kirwan map. So let's see what happens now in the case of toric variety. So M now is Cn and G is U1 to the K. And Hg of M, well, M is contractible to a point. So I only have 0 forms here. And so this is the same thing as polynomials on G, which are G invariant. So that's just polynomials on the Lie algebra. Let's call them T1 up to Tk. Okay, so now I have the Kirwan map, which sends Hg of M to H of M red. But this Kirwan map is the same on these polynomials as the Kirwan map. Yeah, the question was, is it homotopy invariant? So it's homotopy invariant for equivariant maps. So in particular, a particular example of an equivariant map would be, I can just take the map from M to itself, given by multiplication by lambda in C. And as lambda goes to 0, this gives me a deformation retract of M to a point, which is homotopy, which is equivariant, and so induces an equivariant homotopy equivalence of Cn with a point, its origin. And any other questions? Okay, so what does the Kirwan map do here? So it takes Ti and it maps it to the curvature, the ith curvature of the bundle. So that means that the first term class of the line bundle, which is given by I just take the ith factor in not S1, excuse me. This is a G acting. And so what is this? Well, this bundle has this line bundle has a section which is given by slightly confused now. If I take yeah, this is not quite right. Okay, so I have these sections which are given by the ith factor of C. So this will be the image of the ith basis vector. So polynomials on Rn. Maps to G dual. So linear functions. And the ith factor in Rn. Let's call that Si. That's going to map to some linear function on G, and that's going to map to this C1 of the line bundle in this decomposition. And the zero set of this section so you're setting the ith coordinate to be 0. This is exactly phi rad inverse of the ith facet of the polygon. So Kirwan surjectivity tells you that the cohomology of M red is generated by the inverse images of the facets. Okay, and these linear relations that we talked about before, that's exactly the kernel of this map from R to the G. That's saying that there are different ways of realizing these linear functions on G and in terms of linear functions. So that's just another way of seeing the generation result. Let me give another example. This is a non-abelian example. I can take the Grassmannian, and I can think of it as the symplectic quotient of the space of holomorphisms from Tk to Tn. I won't go into the details. It's not hard to work out that this is the symplectic quotient that I get. And so again, the Kirwan surjectivity tells you that if I take equivariant cohomology upstairs, which is just the equivariant, the invariant polynomials on the Lie algebra, then this surjects onto the cohomology of M red. So the cohomology is generated by the image of the Chern-Bay map. Another way of saying that here is that the characteristic classes of the universal bundle have to generate the cohomology. Okay, well, I'm out of time, so I'll have to stop there.
So let's thank Chris now. Any questions here?
Can we go to the previous slide, actually? Oh, there's a question in the chat.
Oh, can you get the theory and GM
Yeah.
value from the last example?
So there is a, do you see the question? Yeah, so.
Yeah, I mean, it requires more work to get the theory and GM value formulas. I mean, that's really about the relations. I mean, eventually, yes, but it's not immediate.
So, so in this slide, you said something about the kernel of the Kirwan map in the toric example. Did you, or did I just mistake?
Yeah. So the way to think about it is that so we have this map from polynomials on G to HM red. But remember, G is the group that you're modding out on, right? So so the space of polynomials on Rn is much bigger, right? So there are two kinds of relations. There's a kernel here when you go from polynomials on Rn to polynomials on G, and then there's a kernel here when you go from polynomials on G to M red. It's maybe easier to think about an example. So in the case of P2, I have these three divisors, which correspond to the three facets of the polytope. And when I go to polynomials on G, I just have a single generator. So that corresponds to the generator that we were calling L before. And then I go to HM red, and this is R of L modulo the relation L cubed equals 0. So the linear relations in the Danilov-Jerkovich theorem appear as kernels in the first arrow, and then the nonlinear relations appear when you take the kernel of the second arrow. Does it make sense?
Yes. Yes.
I mean, yeah. In the Danilov-Jerkovich theorem, you're starting with a set of generators which is much larger than just polynomials on G. So the first thing you have to do is map them to polynomials on the smaller space, G sitting inside the Lie algebra, U1 to the n, which is Rn. And that's going to induce some relations right away, even before you go to the symplectic quotient. But because the only thing that you're doing here, I mean, this map is just combinatorial. It's not hard to see that what the kernel is. Just sometimes you have, the same linear function on Rn induces different functions on Rn induce the same linear function. That's the only.
Okay, and are there other questions? Okay, so in the last few minutes we have, can we actually go back to the Grassmannian example? You were about to say something which was cut off by the time ending.
I was just going to write down a couple more details about how you get this as a symplectic quotient. So the moment map here has to go to the Lie algebra of G dual. I can identify this with G in the standard way. And then the map here is something like A goes to 1 over 2i, A star A, something like this, depending on how you identify with dual. And so then I can subtract off an invariant constant here in the moment map. So I could subtract off, say, the identity. Okay, and then phi inverse of 0 is going to be matrices so that A star A equals the identity. So these are K by N or N by K matrices whose rows or columns form our Hermitian basis. And but then you're modding out by the action of G. And so when you do that, you know, and two matrices are going to be equivalent if and only if they have the same row space. And so you just get the Grassmannian split. And so that then Kirwan surjectivity would tell you that the homology of the Grassmannian is generated by these invariant polynomials. But then, as Ritwig said, they're going to be relations. And again, they're not. It's not hard to see what the relation should be. You know, for example, in the Grassmannian case, what you usually do is usually say, well, the universal bundle plus the quotient of the universal bundle. This gives you the trivial bundle, and then you say, well, the characteristic classes of the trivial bundle is 0, and that gives you a whole bunch of relations. So, that takes more time, not just 2 minutes.
Thank you. Thanks again.